We will start our discussion. This is our first session on Verilog. So first, I want to give you a brief idea about VLSI design flow. Okay. So we will take the example of a basic full adder circuit. I hope you are all aware of this full adder circuit, right? Uh, do you have idea about full adder circuit? Everyone has idea about full adder circuit, right? What is full
Yes,
adder?
sir.
Yes. So basically, a full adder will have three inputs. Let's take this is our full adder circuit. So it will have three inputs: A, B, and Cin, and these are our outputs: sum and carry. So this is nothing but a simple full adder. Okay. So if you I'm taking a basic full adder circuit, and if we want to design this full adder circuit, and I want to relate this with our VLSI design flow. So in the VLSI design flow, the first step is design specification. Okay, so what is the first step? If you want, you can write your running notes, or I will share this PPT. Okay, anything is fine. So the first step of VLSI design flow is design specification. That is, we are going to specify what and all the inputs and what and all the outputs of a design. So in the case of full adder, we are going to specify what and all our inputs are A, B, and C, and what and all we have as the outputs. So that is nothing but our design specification. And coming to the next step, which is behavioral description. That is, we are going to describe our behavior of a particular design. So what is the behavior of this full adder? Can anyone tell me what is the behavior of this full adder?
Perform the addition.
That is what we are going to specify in the next step. That is nothing but behavioral description. So in the case of behavioral description, we are going to give the description of the behavior of a particular circuit. In the case of full adder, what is the behavior? Behavior is nothing but it is going to perform the addition between the inputs A, B, and C. Okay. So that was the second step. So first step was design specification, and the second step was behavioral description. And the third step, where we are going to use our Verilog language, is RTL description or HTL. Okay. So in this particular step, you can use two different languages. That is, one is Verilog, or also you can use VHDL. Okay, VHDL. Okay. So in this particular step, you are going to use this particular language Verilog, or you are going to use VHDL. So these are the two programming languages which are available for programming or for writing the RTL description, register transfer level. That is, you are going to write the code, okay, the behavior of the particular design in the language in the Verilog or VHDL. That further it will be converted into the gate level netlist, and it will be converted into the hardware. Okay. Now, so this is the third step, and after this step, if you can see, the next step is functional verification and testing. That is, the code which you have written, you're going to check whether the functionality of the code is correct or not. Okay, for example, if you have written the Verilog code for this full adder, you are going to check whether the code which you have written is and testing. Okay, so basically, functional verification and testing is nothing but the code which we have written. Okay, the Verilog code which we have written, we are going to verify whether the functionality of that particular code is correct or not. That means if we have written the code for full adder using Verilog, okay, whether our code is giving the same functionality what we are expecting. Okay, whether our code is working according to our functionality or not, according to the functionality what we are expecting or not, that we are going to check using this in this step. Okay, functional verification and testing, we are going to write the test benches for this. Okay, that also we are going to discuss in our upcoming sessions. We are going to simulate it, and we are going to check in the waveforms. Okay, so if you install or if you use any tools, EDA Playground or Vivado or Model so using the tools, in that we are going to, with the help of the simulation windows, waveform windows, we are going to do the functional verification and testing. Now, after that, if there are any bugs which are found in functional verification and testing, okay, so you can see the arrow mark which is pointing reverse to the RTL description. So if you found any bugs in your code, in your particular code, in this particular stage, functional verification and testing, you're going back to the third step, which is RTL description. Okay, so if you find any bugs or any errors in your functional verification and testing, you're going back to your RTL step, which is HTL, and you're going to modify your code accordingly, and again you're going to perform this step. Okay, so this particular third and fourth step will be repeated continuously until your functional verification and testing has been successfully completed. Okay, so up to here, is it clear for everyone? We are also going to do. Okay, so we are going to write Verilog code for a particular design. Okay, or for a particular specification, we are going to write the Verilog code, and we are going to write the test bench, and we are going to check the waveforms. Okay, we are going to check the functionality of that particular design what we have written in the Verilog. So we are going to check it. If we find that the particular design is not working as per our requirements, we are going to change the code. Okay, we are going to modify the code. Okay, until our specification or our functionality is met, we are going to do this third and fourth steps repeatedly. Okay, so after this, after everything is correct and everything is passed in the fourth step, we are going to logic synthesis. We are going to logic synthesis. So what is meant by synthesis? Can anyone answer this particular question? What is meant by synthesis?
So synthesis is the process of converting Verilog into netlist.
Yes. Okay. So the code which we have written, the Verilog code which we have written, will be converted into the hardware. Okay, or the gate level netlist. Okay, that process is known as synthesis. Okay. So in the here in this particular step, logic synthesis, the code which we have written, for example, here the full adder code which we have written, that particular code will be converted into logic gates. Okay, that will be converted into logic gates. That also we will see the Vivado tool. I will show you how to perform this logic synthesis part. Okay, so in that particular tool, the EDA tool only will convert this particular code into the synthesis. Okay, logic synthesis, and that particular logic synthesis, after that we have gate level netlist. Okay, we have the gate level netlist, that is the description of all the code which we have written in the form of gates. Okay, so that is nothing but the gate level netlist. The file will be generated, and after that, so up to here, and after that, again logic verification and testing will be happening. So up to here, this is front end part. Okay, so this is front end. And from floor planning and physical layout verification implementation, this is all backend. So in the VLSI also we have two phases. One is front end and another is backend. Okay, so backend also has separate tools for it, and the layout design, everything we have. And front end, we have different tools, and we use Verilog or VHDL. And yeah, so this is about VLSI design for front end and backend. So up to here, is it clear for everyone? Shall we move forward?
Yes, sir.
Yeah. So this was the definitions which I was saying orally. So design specification is nothing but defining the functional requirements and performance criteria. In the case, we are taking full adder circuit, and these are the design specifications. We are specifying the inputs and outputs, and here the Verilog role is not much, and synthesis is nothing but converting the RTL Verilog code into gate level netlist that can be physically implemented on silicon. Okay, so that is meant by synthesis. And we are going to use synthesis tools that will convert Verilog RTL code into logic gates and or XOR. Okay? And in this particular example, we are converting full adder's RTL logic into a specific technology library. Okay, and running synthesis checks to confirm that the synthesis netlist meets the timing and design constraints.
Sir, technology library means what here?
In the front end, we are not going to focus mainly on this technology. Okay, irrespective of technology, Verilog language works irrespective of technology. Okay? Mostly this is taken care in the backend only. Okay, like a 3 nanometer, 1.5 nanometer, we have different type of technologies, right? Is it okay?
Okay.
And Verilog is used to represent the RTL code, which is the synthesis tool that interprets to create the gate level representation of full adder. Okay, so that is what we have discussed till now. So the code will be converted into the gate level netlist by the tool itself. Okay,
Excuse me, sir.
yes, yes. So that was the introduction to the VLSI design flow. So let us start with the modules. Okay, so a module in Verilog is declared using the keyword module. So a module, it is a keyword. Okay, and we are going to declare it at the beginning of the block, and we are going to use end module. Okay, so module as well as end modules are the keywords. So any code, any design, if you want to write, you are going to start your design with the keyword which is called as module. Okay, and followed by end module. Okay, so these two are our keywords. These two are our keywords, and module followed by any name. Okay, so in the case of full adder example, I'm going to give some name, full underscore adder. Okay, so this is the name of my module. Okay, whereas here module and end module are my keywords. Okay, so a module in Verilog is declared using the module keyword at the beginning of the block and ends with the end module keyword. So the module has a name, or you can say identifier, and a list of terminals that describe the input and output ports of the module. Okay, so identifier. So here the full adder, this is a name, or you call it as a identifier. Okay, so it is also known as identifier, or it is also the name of the particular module. Okay, and so this is the syntax for a module declaration. You can note it down or you can take a screenshot. Module is a keyword followed by end module keyword followed by module name. You can give any name, but there are some restrictions or some rules to follow when you are giving your module name that we will discuss in our upcoming slides. And coming to this module terminal list, I will discuss now only, and followed by the internal code which you are writing. So the code which you are writing will be between in this module and end module only. Okay, in between your module and end module, you are going to write your Verilog code. Okay, so after completing your code, you are going to write end module. So these two are your keywords. Okay, so up to here, is it clear? Let's see what is meant by this module terminal list. Let's take our design, the full adder example only, what we were discussing previously. So this is our full adder. These are our inputs and these are our outputs. Okay, so for writing this design, you are going to declare your keyword, or you are going to use your keyword followed by identifier, that is a module name. You can take any name, but there are some rules we will discuss further. Okay, here I am taking fa. Okay, now followed by brackets. Here you should give your terminal list. Terminal list is nothing but your port list. So what are all the input ports you have? These are your input ports. Let me name it as ABC, and output ports are some and kind. So these ports you are going to specify here inside this terminal list. Okay, so you have another keywords which are known as input and output. Okay, so these are all the keywords. I'm writing it here. So using these keywords, you are going to mention your terminal list. Here inside the brackets, you are going to mention your terminal list with the help of these keywords. So what are all the inputs for your design? Can anyone tell me what are all the inputs for your design?
A, B, and C in.
A, B, and C. So you are going to mention A, B, and C in as input. Okay, you are going to use this keyword input, and you are going to mention A, B, and C are inputs of your design. And you are going to use this output keyword, and you are going to tell that S and C are outputs to your design. So this is how you are going to mention your module terminal list. Okay, with the help of keywords input, output. Okay, so these two are keywords which are used to tell what are all the input ports and what are all the output terminal ports. Okay, and you have one more keyword which is called as in out, which is used to tell whether a particular signal is acting as both in and out. Okay, so these are the three keywords which we have to declare inputs, outputs, and in outputs. Okay.
Sir, this in out is actually used in designs like
Yes, yes,
because
yes, it is used.
okay, because I am not aware of any scenario where I come across this. So
Yeah, we will see one scenario. Okay.
okay.
Now, let us see the rules for declaring a module in Verilog. So, a Verilog module is declared using the keyword module that we have already seen and ends with end module. The module name must follow the module keyword and should be a valid identifier. No spaces, no special characters except underscores. That means your module, let's say this is our module, and the identifier, when you're writing your module name, there should be no spaces. Let's say full adder, you cannot write full space adder. Okay, so this is an invalid representation of your name, module name. Okay, so you can use underscore, underscore is valid. Let's say module full underscore adder, like this you can use. Okay, so except expect underscore. Okay, except underscore, no other special characters are used when you're writing your identifier name, like dollar, okay, or hash. Okay, all these special characters, percentage, this all special characters are not allowed when you are declaring your identifier or the module name. Okay, so please be careful when you are declaring your uh, module name. Okay, so this is what, and spaces are also sorry, and spaces are also not allowed when you are declaring your module name. And one more thing, the first letter of the module should start with a letter only. It should not start with any special character or underscore or any number. Okay, any number like 2 full underscore adder, like this also, it is not valid. Okay, so please be careful. You can use numbers in between, but you cannot start your module name with a number. Okay, so these are the rules. So this is how you are going to create your module module underscore name, input port list, output port list, in out port list. You are going to write your code here in between, and you are going to use end module. Okay, for full adder, what you can write, module, the design name you can write fa, and what are all the inputs you have, abc. Okay, input a, comma, input b, comma, output sum, and you are going to write your code here, and you are going to use end module. Okay, so this is how with the keywords input as well as with the keyword output, you are going to mention, you are going to specify what are all the inputs and what are all the outputs for your particular design. Okay, now
Sir, scene will be also as input, right? Scene and see out will be the.
input, scene, and output. Okay, so this is a 1 minute. So this is how you are going to mention your inputs and mention your outputs of your particular design. Okay, now, so the module name must have a unique name that is a valid identifier. You can use this representation, full adder, or small representation, anything you can, any case you can use small letters or capital letters or mix of small letters and capital letters. Okay, coming to the port list, which I said already, we have different type of keywords for mentioning the ports. One is input keyword for mentioning input ports, and output keyword for mentioning output ports, and in-out keyword for mentioning in-out ports. Okay, and the port list is also optional in some cases if the ports are declared within the module body. For example, in the case of test benches, we are not going to we are not going to give any ports. Okay, for only designs we are going to give the ports. The test benches also we will see. Okay, so in the when we are developing the test for when the variable is working both as input as well as output, we are going to give it as in out, like it is a bi-directional bus. Okay, let's say suppose here this is your particular design. This is your design. For this design you have some specific input ports and you have specific output ports. And if there is a port which is bidirectional, that is it is acting as input as well as it is acting as an output. So in this particular case, to model this particular case, you are going to use in out.
Yes.
So this particular signal will act as an input for this design as well as it will work as an output for this design. Okay, so to model this particular signal or variable, we are going to use this keyword in out. Okay.
Okay.
Yeah. So this is how you are going to create your module, and you are going to create the ports. You are going to create whether the signal is particular input to your design, or output to your design, or in out to your design. Okay, now, and for declaring the internal signals, you have different data types. You have one is wire, reg, and integer, that we will see in our next session. Okay, we'll discuss about this in data types: wire, reg, integer. Okay, we have different data types we have, and what is the use cases of this data types, everything we are going to discuss in our next session. Okay, so in this particular session, we have started with the introduction to Verilog, and we have also seen the VLSI design flow, and we have started with the modules, and we have seen the keywords, what are the keywords, and if we have a particular design, how to give the inputs, outputs, and inouts for a particular design. And we have also seen the rules for declaring a module, and yeah, and we have also seen the port list for the how to give the port list. Okay, so that is what we have seen in this particular session, and in next session we will start with the keywords. We will see what is meant by wire, what is meant by reg, and what is meant by integer. Okay, so and we'll start with different type of abstraction levels which are present, and we will see what is this different type of abstraction levels we have. And after that we will start with the basic constructs.